Okay, now there are a bunch of statements we can make based on the reduced form of the matrix. Okay? First of all, say matrix reduces to this form. Okay, what's this say about the corresponding system of simultaneous equations? Well, you see you got a free variable. Actually, you got two. Okay? Because if it's x1, x2, x3, x4, x4 is free and x2 is free. Okay? There's no unique solution of whatever that system was. Okay? And actually, I mean, if this is a system, it's actually an augmented system. Okay? So being, you'd have one free variable. So I actually misspoke when I said there were two. Okay? I was assuming this is your coefficient matrix. Okay? Not an augmented matrix. But if it represents a system, it is a coefficient matrix. So that would be one free variable. But you can imagine there's another column, in which case you have that. Okay? It tells you there's no unique solution. One row is a linear combination of the others. At least one of these rows is a linear combination of the others. Okay? In the original matrix. If the matrix is not augmented, then we're not in the context of simultaneous equations. And that would say that the homogeneous equation for this coefficient matrix would have two-dimensional solution space. Okay? I was a little careless when I read some of those comments. Now, what we're really getting at, and of course the section in the text will pull all this out nicely, the columns of the original matrix, because I was really trying to talk about two things at once, which is why I missed all I do with the augmented matrix representing the system. But the columns of the matrix form a set of linearly dependent vectors. Okay? And they turned out to be equivalent to well, okay. If you take all the columns of the original matrix and write them down, then as you know, because we've done that sort of thing with a set of vectors, and you mentioned linear independence right away. Okay? So it's the column vectors that are linearly dependent. And also, since you've only got two leading ones here, the column vectors are not only linearly independent, but they reduce to a set of two linearly independent vectors that's with the same span as the four columns. Okay? And the same can be said for the rows. They've only got three rows. Okay? But they can be reduced down to two rows that are linearly independent that span the same thing. Okay? So we can make the same comment, even though the sets have different numbers of vectors. And then we can say that the dimension of the row space equals the dimension of the column space, because of course the dimension is just the number of linearly independent vectors necessary to span the set. Okay? And then we make a definition that the rank of a matrix is the dimension of the row space. Now, if you're given a matrix, how do you find the basis for the row space? Okay? Well, it's pretty easy. There's a theorem that says that two row equivalent matrices have the same row space. We'll talk about why that is. But it's just comes down to the fact that the elementary operations don't change the span of the rows, okay, the set of rows. And it's really easy to prove that. It's really obvious when you take the three different row operations and see what they would do to the space span by the rows, okay? So two row equivalent matrices have the same row space. And very similarly the same column space, okay? So now I'm starting to think if that's even true. We'll leave that as a question mark, okay? Because that takes a little thinking. Okay, so to get the basis of the row space, produce the matrix. Okay, you'll end up with a basis. Because what? Okay. What's the basis of the row space here? Well, clearly it's this row and this row. I'll write these as row vectors. Okay? Because these are clearly linearly independent. If you have leading ones in every column that isn't all zeros, they have to be linearly independent, because no way any multiple of this one can have a 1 here. So this is clearly not a multiple of this, right? And if you had another row with a leading 1, say here, well, no sum of multiples of this row and this row could give you 1 here, because you got nothing but zeros below each leading 1. So it's very clear. Okay? Make sense? If you accept this, which is easy to prove, okay? So you have a method for finding a basis of the row space of any matrix. And of course, the row space is important because that thing about the 4 fundamental subsets, okay, or subspaces. The row space and the null space, okay? and then the range space and the inverse of the transpose. We've talked about all that except the last. And that structure is extraordinarily important in a lot of applications. Okay, we'll see that. Well, okay, let's look at some of the problems at the end of this section. Then we'll talk about the nullity.